In this video, we'll be discussing some of the design principles that are present and often considered when designing experiments. So there's a few different basic strategies that can be taken advantage of, or that are often implemented, I should say, in an experimental design. One of which is something that at first glance sounds really bad, but maybe a little better than we think. It's a best guess experiment. So this is used a lot, and pretty much we're just trying to guess what the proper levels are and see and kind of use that. So the experiment is designed using, say, an expert who's guessing what the experiment should be or what tests we should particularly run. Now, the primary disadvantage of this is that your guesser could be really bad, and that there isn't an objective format for how your tests are being constructed. That said, this is a lot more successful than you may expect. The input of an expert in a particular field can be quite valuable, and more valuable than we often like to think. So this isn't as bad as it may sound, that we're just kind of guessing as to how we put the test together. It sounds pretty bad when you say it like that. But it is a little more successful than you may suspect. That said, there are enough disadvantages here that we probably don't want to go down this route. And the biggest one is that even if you think you have an expert, sometimes they're wrong, and the degree of expert and the quality of expert directly impacts the quality of the tests and the results that you'll be able to claim from the test that you run. Another type of experiment is called an OFAT experiment, which stands for one factor at a time. And sometimes this is associated with like a scientific or engineering method. And pretty much what we do is, let's say we're studying an experiment that we have multiple factors that may come into play. So I mentioned earlier in a previous video an experiment cooking cookies where I'm going to make some chocolate chip cookies, and I want to see how good they are when they come out. And so I'm going to cook them at 200 degrees, 300 degrees, and 400 degrees. So that's one variable or one factor. But let's say I'm also interested in a second factor, and that's how long I cook them. So I'm going to cook them for 5 minutes, for 10 minutes, or for 15 minutes. So if I do one factor at a time, so let's say I cook them at, so just one factor, so that means I'm not going to change the other one. I'm going to do one at a time. So I'm going to cook them at 200 degrees, 300 degrees, and 400 degrees for 5 minutes. And then I'm also going to test that time, where I'm going to cook them at 5 minutes, 10 minutes, and 15 minutes at 200 degrees. And then I'm going to pick the best. And what's going to end up happening is that the best time is going to be 15 minutes for the best quality of cookies, because if I'm cooking at 200 degrees, then they're going to need to cook at least 15 minutes. And that the best temperature is going to be 400 degrees. And so my conclusion for that experiment with the one factor at a time experiment is that I want a cookie that's cooked at 400 degrees for 15 minutes long. And clearly you can see that that is just not going to be the case. That cooking at the highest temperature for the highest time is probably going to give me some very, very black chocolate chip cookies, and that maybe that's not what I would particularly want. So that effect, incidentally, where one variable, say temperature, affects another variable, say how long I should cook the cookie, is called an interaction, and that really devastates the OFAT experiments. Another thing about the OFAT experiments that you may not consider, and really isn't clear until we get more into experimental design, is that they're very inefficient with the experimental units. So I would have to do 3 sets of cookies for the temperature and 3 sets of cookies for the time, and they'd have to be a different, I need 6 sets of cookies total. Whereas if I combine them, sometimes I don't need as many, especially with some of the designs that we'll talk about near the end of the class, called the fractional designs. Now, this last one, statistically designed experiments, are probably what I would consider to be the best on this list. They're designed based on Fisher's factorial concept, which really looks at mixing all of these different things. So maybe for one batch of cookies, I have them at a particular time and a particular temperature, and I mix all of the independent variables and take them all into account when I'm looking at every single experimental unit that I'm doing. So I don't separate out one factor at a time, as in the OFAT experiments. What I'm doing is that for every experimental unit, I'm accounting for all of the factors at the same time. And this can lead to much more efficient experiments. But the other thing that it does, in addition to just general efficiency, is that it can be really, really powerful to determine the presence of and effects of interaction. So for the strategy, we're looking at a couple different concepts here, because we can either do a comprehensive strategy, and so for comprehensive strategy, what I mean is just a single large experiment. We're just doing a really, really big experiment. And this is what most people think of, honestly, when they think of experimental design, is these comprehensive experiments. The problem is that if I just set a whole, I put in $100,000 and I'm just going to do a huge experiment, and I'm just going to do it all in one big go. If things go wrong, it doesn't allow room for things to change. So these comprehensive experiments don't really allow things to evolve. If things go really, really wrong or really, really right, I'm kind of committed from the start. And this commitment from the start, again, makes me pretty unflexible. That said, not all is bad. Again, many people think of these as the main way to do them, and one of the good things about it is it takes less time. So if you're really crunched for time and have a whole bunch of money and resources to burn, then you may as well try to come up with an experiment that accounts for all the different possibilities right away. Again, the risk is you miss some possibilities, or if maybe the experimental protocol is wrong, you mess a whole bunch of things up and don't really have time or resources to go back and change. Now, this is in contrast to a second type where we do it sequentially, and that is we do multiple small experiments and just stack them on top of each other. So let's say that cookie example. Let's say that the first example I did was I wanted to cook at 100 degrees, 110 degrees, and 120 degrees. Now, if I had done a comprehensive experiment, that is, I did the whole experiment like that, and I put all of my cookies in at these temperatures and just made a really, really big experiment, what would that do? Well, if I cook cookies at a max temperature of 120 degrees, they're not going to come out very good. And if I just used all of my cookie dough on making such cookies, I don't have room to change that. I just already messed it up and I used all of my resources, so now I'm kind of up a creek. However, if I use the sequential method, I might be able to do a small experiment with a few, and then I see, man, all of these cookies sucked, but it looks like the more heat, the better they're getting. Maybe I need to up the heat a little bit more and adapt on the fly. Now note that because I'm not sticking all of these cookies on a pan, this may take more time. So I don't have 30 cookies on a pan at each of the temperatures, 100, 110, and 120 degrees. I just have one cookie on each of the pans. So I'm doing multiple small experiments, and I shouldn't just have one experimental unit on each of the conditions. Typically, we do have replication even when we do the small experiments. The idea here is that I'm not using my whole thing of cookie dough on a single, I shouldn't even say a single run, but I'm not using all of my cookie dough in the experiment without allowing time for tweaks and adaptations. Now, I should mention here, though sequential tends to be recommended, it's important to realize that not only does it take more time, but it also, if you make changes, you've now changed the nature of the experiment. And so now your replications are a bit thrown off. You don't have as many replications under the final conditions. Now, this tends to actually not be as bad as we think, because if you have to change the conditions, if the initial conditions were so wrong or the initial procedures were so wrong, such that they necessitated change in the middle of your running experiments, and again, you're running these multiple small ones instead of a single large one, then having more replication, the decision you're making is more replication under the initial conditions better or worse than having less replications under the adapted conditions? And if you have to adapt, and there's many cases where you would have to adapt because something just went so wrong it's not going to work out, then at least you have some sample under a procedure that is going better and does work out. Because throwing all of your resources, again, if I cook cookies at 100 degrees, 110 degrees, 120 degrees, that's so wrong that just none of them are going to taste good and nothing's going to work out. So if I had to change and I did multiple experiments, yes, I may have a smaller sample size at the end of the day under the conditions that make more sense. Let's say cooking them at 300 degrees, 325, and 350. So I might have a less sample size under those realistic conditions. But if I had ran it as one large experiment, I would have had a sample size of 0 underneath those alternate conditions. So what this allows you to do is, if you make smart adaptations and don't change for minor things, really make sure a change is necessitated if it is, then it lets you get the sample size in areas of the factor that you really want them to, using procedures for the experiment that make sense and make sure you have success. So don't be afraid of making a change in multiple small experiments if you have to. But that doesn't mean that you should be making changes all the time just for little small things. You want to make sure that any changes or tweaks you make is weighed against the cost of sample size, because you shouldn't combine samples or results of different procedures that are used in an experiment if you end up changing procedures. I guess it's also important to note here what I mean by large and small. So let's say we're doing a class experiment and I don't know, making paper airplanes or something. I'm not saying that you should do it, that you shouldn't do a small class experiment altogether, that you should really break it up and make it a painful, long experience. This is more for an industrial level experiment where, let's say I'm doing something that involves raw pure gold, where I would actually waste a lot of money were I to just blow through things and not get useful results. So something that takes a lot of time or costs a lot of money, that's where this distinction is more important. Something that really didn't take a lot of time and didn't cost a lot of money, it's less important to make this distinction, because the adaptation, let's say it took virtually no time and cost virtually no money. Well, if I ran it all together and it didn't work out, then I could just make tweaks and run it all again. So the adaptation is already built in there. However, again, on a very timely procedure, sometimes it's nice to build in breakpoints, call it the conclusion of an initial experiment, and then see if any adaptations need to be made. And again, that tends to be what's recommended, but it's important to realize that some of the limitations, even with the sequential approach, and then the fact that for something like a course project, that it might not be needed. All right, so in social research, design of experiments takes on a little bit of a different meaning, and so I wanted to talk through this because very often we use maybe the industrial definition, but social researchers are also very invested in design of experiments and have a bit of a different view. So in design of experiments in the social research, it really focuses on random assignment, and if you think about it, random assignment and the ability to control the independent variable are the same thing. You can think of assigning the experimental unit to each of the groups in the independent variable, or you can think of assigning the groups in the independent variable to the experimental unit. And it really doesn't matter how you look at it, but again, both of these, the ability to control the independent variable and the ability to assign experimental units, actually are the same concept, just phrased from a different perspective. One is phrased from the independent variable, looking at the experimental unit. One's phrased from the experimental unit, looking at the independent variable. And if that doesn't make sense, just pause it, maybe replay this section, think about it for a second until it kind of clicks. The idea here is that it's random, though, that as I'm doing either assigning levels of the independent variable to the experimental unit or assigning experimental units to the levels in the independent variable, that process happens randomly. So very often in social research, our goal is to look at a particular treatment and to see how it affects a particular outcome. So we look at, did the outcome improve? Did the outcome, is improvement going up? Is improvement going down? Um, and that's where the idea of growth. So let's say math ability, it's a classic example. At least for me, I'm an old math teacher. So did your math ability increase because of the new curriculum? So another thing in social research is very often we really like to use a comparison group. And we'll talk about that in just a second, but the use of a comparison group really is when we talk about controlling the independent variable, if I'm testing out a new way of teaching, how do I compare if that's better or worse than the old way of teaching? So the comparison group in an example like that might be the old way of teaching. So if I'm teaching a math class, I might teach two. I may teach one under the new way of teaching, one under the old way of teaching, and call the old way of teaching a comparison group so that I can later compare. All right, so the designs are often written in terms of R's, X's, and O's. An R means a random assignment, an X means treatment, and O means observation. So R is randomization, X is treatment, O is observation. So if I'm just doing a single measurement for a treatment-only group, I would do the treatment, and then the single measurement would be after the treatment. Now, if you think about this, what are you going to learn from that? Well, maybe nothing. So I see that the math final exam, after I did my new test, I had an average of 90. Well, is that good? I don't know. So that's an important thing to realize, is that a single measurement can be kind of limited, because one of the things I don't have if I just have a treatment group is nobody to compare to. So I could have a treatment and control group. The treatment group has the treatment and then an observation. The control group doesn't have that treatment, or it has a different treatment and then the observation. And then when I say, okay, I did one course with my new curriculum, one course with the old curriculum. The course with the new curriculum, the average score was 90. The course with the old curriculum, the average score was 80. Well, because I have something to compare to, I can say the course with the new score had a higher average score than the course with the old score. Now, one issue that comes up here is, well, why is that the case? Is it because of the treatment? Well, in this particular case, I really hope it's because of the treatment. But one other thing that could be happening, and I don't have any evidence if it's the treatment or this other thing, is that maybe students in my treatment group were just better students than students in my other group. Like if I'd have compared them, even if I hadn't done my super special curriculum, this class would have still gotten a 90 on the final, and this class would have still gotten an 80 on the final. So how do I provide evidence against that? Well, there's two ways. One is I could randomize. So I could randomly assign students into the treatment and control group. And if I randomly assigned students into the treatment and control group, well, ideally, randomly, because I am not allowing the better students to be in the treatment group, then there wouldn't be a difference in their score. So I'd randomly assign and then do the treatment in the treatment group and not do the treatment and control and then do an observation at the end. And this would be an experimental design. One question, though, is did random assignment really work? And that's where we get into these pre-post designs, where I look at the students not just after I've given the treatment, but also before I've given the treatment. So in this case, with a treatment only, I'd look at students before the exam, students before the class, do the new treatment class, and then look at students after the class and look at how much they grow. And I mentioned earlier we focus a lot on growth or maybe shrinking the number of problems they got wrong, growing their average percent correct score. It really depends on how you look at the problem. So shrink or grow, just depending on how you phrase the problem here. Both are fun. And so what I can show is that because of the treatment, or at least in my example due to the treatment, it looks like the post is doing better than the pre. So students after the class are doing better than they were before the class. Now for the second one here, where I've got a treatment and control, this is a second way that I can try to justify, well, the students in the treatment class and the students in the control class aren't all the same. And actually, this is a decent method to take advantage of when you aren't allowed to randomly assign students. So for instance, students are allowed to pick the class, but if I look at how the students scored at the beginning, then I can kind of get a feel for, okay, these students don't really have a different score. Now, one threat that remains, even as students walk in with the same basic math ability, is maybe the students in the treatment class are just better learners. So that's why they would have gotten a better score at the post. It's not because they had a different score at the beginning, but because they're better learners through the semester. And that's where randomization can still come in, where I randomly assign individuals to the treatment and control groups. Then I look at the pre-scores to make sure that they're pretty leveled out, that random assignment worked, and then give the treatment to the treatment group. Don't give anything or give the regular old thing to the control group or anything else you want to compare to the control group, and then look at the final scores. And again, what we tend to do here if we have a pre and a post is I don't really want to look at are the final score different. If I'm teaching curriculum, I want to look at did the students grow differently. So is the post minus the pre different in each of these groups? So this is one of the things that we do in social research. And again, in industrial research, we don't particularly talk about it all the time, but in social research, it actually is pretty important. And that's because in social research, we really, really, really want to make sure that we are looking at the thing that we want to study. And this is where the random assignment really comes in. The other thing in social research that I actually should have mentioned is that in social research, very often we're studying people. We're studying the interactions of individuals, and our experimental units tend to be people that we study. All right, so let's jump into a quick example of a factorial design. This is one from your textbook and is kind of fun. So in a factorial experiment, we're looking at all of the different possible combinations. And so I mentioned factorial experiments earlier as being the primary method. So we're looking at all of the combinations. And I talked about cookies earlier, where I want to look at all of the combinations of the temperature and the time. I want to look at all of them, not just looking at one of them for a fixed level of the other one. I want to look at all of them under all of them. Now, in this particular experiment, we're going to be looking at golf. So in golf, what are the different variables that could have an effect on a golf game? Well, we could have a different type of driver. We could have a different type, which is a type of golf club, a different type of ball, and all these other things that we could be doing that could affect someone's golf game. So as we're looking at this, if you just think about two levels under each of these factors, the type of driver, we could have, say 2 types of drivers and 2 types of balls. And when I say we want to look at all of the possible combinations, that means the first type of driver with the first type of ball, the second type of driver with the first kind of ball, the first type of driver with the second kind of ball, and the second type of driver with the second kind of ball. We want to look at all 4 of these pieces, and this is one way that you can visualize that. Now let's say we did 2 replications. So note again on the graph, this isn't like an XY axis graph in the sense of being higher doesn't mean being better. This is a factor graph. So the height of these dots literally means nothing. So please don't get that confused. What means something is the numbers. So the numbers are the scores on the golf game under these different conditions, and we played 2 different golf games with the first kind of driver and first kind of ball, 2 different golf games with the second kind of driver and the first kind of ball, 2 different golf games with the first kind of driver and the second kind of ball, and 2 different golf games with the second kind of driver and the second kind of ball. So that's where these 2 numbers are coming from, is the scores from each of those golf games. Now, if I want to look at the type of ball, then the type of ball, the first one versus the second one, I want to look at this first line versus the second line. So the average score I got with this first line across both drivers and the average score I got on the second line across both drivers. If I want to look at the type of driver, instead of looking horizontally, I want to look vertically. So I want to look at the scores I got with the first kind of driver across all of the different kind of balls, and the scores that I got with the second driver over all the different kind of balls. And I'd be looking at the average score with this driver and the average score with this driver to compare. So it kind of makes sense, right? If I'm looking at the type of ball, then I want to look at the first ball score versus the second ball score. If I'm looking at the type of driver, I want to look at the first driver score versus the second driver score. And then if I want to look at the interaction, so what if some balls work better with some drivers? Then what I look at is the diagonal, and I'm literally going to take an average. So for the driver effect, I'm going to be averaging the effects from the first driver. So 4 golf games, adding them all up, dividing by 4, and then subtracting 4 golf games, adding them all up, divided by 4. So this is the average score with the first driver minus the average score with the second driver. Excuse me, I think it's actually the average score with the second driver minus the average score with the first driver. Direction doesn't really matter here except for the interpretation of this number. So on average, the second driver had a score of 3.25 higher than the first driver. Same thing here. I've got the second ball, all of the scores that I got with the second ball, no matter which driver they used, divided by 4, minus all of the scores that I got with the first ball, no matter which driver they used, divided by 4, and I get an average difference between the balls of 0.75, which is a fair amount less than the effect of the driver. So the ball effect seems smaller than the driver effect, and we could use statistics to determine that, if that's true overall, or if it was just these golf games that's true for. And then the interaction effect. So that's where I take those diagonals. I take one of those diagonals, and so this would be the first diagonal, bottom left to top right, compared to the other diagonal, top left to bottom right, or maybe these are switched. The positive diagonal and the negative diagonal are switched. But the order doesn't matter here. I'm just taking one diagonal, the scores of all the golf games on that diagonal, divided by 4 to give me the average score on the diagonal, and then subtracting the average score on the other diagonal. And I see that the ball driver interaction effect, that is, do different balls work differently with different drivers, is relatively small, smaller than the effect of the ball or the effect of the driver. Now you can extend this out to multiple factors. We just talked about 2 factors, a ball and a driver. You could do 3 factors. So a 3-factor design, now you don't just have 4 conditions you have to account for, you have to account for 8 conditions. And in general, the more factors you add, it actually has a geometric progression on the number of conditions that you have to account for. It's a very explosive process. That said, it can be a very useful process because we can look at all these different pieces. The 3-factor experiment, instead of having 4 conditions we'd have to account for, and 2 games under each would be 8 total games, just adding one other factor with 2 levels, just one more variable, makes us have to go from 8 games to account for another 4 conditions with another 8 games, so it makes us go from 8 games to 16 total games. And see if you can work out, again, just kind of write some imaginary scores next to this and figure out how many scores you have here, and you'll find you have 16 total scores. Now, you can add another factor. You could do a 4-factor. Unfortunately, we as humans tend to think in 3 dimensions. It's not unfortunate, it's just the way it is. But what is unfortunate is it becomes difficult to visualize multiple factors as we move beyond the 3-factor design. So typically drawing out these graphics is not particularly helpful as we move beyond. A 3-factor can be helpful, the 2-factor can be helpful, but frankly I find them more confusing because the height of the bars doesn't actually mean anything. It's just indicating which particular combination of factors are we using. And we'll talk about some other ways to do that later in the course too. Now, as a peek ahead, there is a way to deal with this intelligently. So I mentioned that these explode out. So we had 16 games with 3 factors. We just talked about adding a 4th factor, which doubles the number of games we'd have to play. So we'd have to play 32 golf games. And though I'd be happy about that, I'm not sure my wife would. So how can we deal with this? And there is a technique in design of experiments called a fractional design, where we can talk about, well, how can we cut these down? And how can we make intelligent decisions about which particular combinations of factors we should be using in order to cut this down in a meaningful way. And what you'll notice is that the ones that we pick on one square or one cube are the opposite of the ones that we pick on another cube, and then we combine them intelligently. So this is a quick glance at a cool design, and this is, I think, very, very cool because it lets us study a large amount of factors, which normally would be very, very prohibitive because we'd have to run so many different replications. But with the fractional designs, again, we can make some intelligent decisions, and that allows us to do this much more efficiently with just a fraction, literally a fraction. That's why it's called a fractional design, literally a fraction of the games that we would normally have to do, or using our language, a fraction of the experimental units. And so if experimental units are expensive, golf game isn't too much money, but it's certainly expensive in terms of time, then a fractional experiment can help us a lot. So this is a pretty advanced design. Again, we're going to talk about it later in the course, but as we're talking about the different setups and ways to visualize them, I kind of wanted to point this out because it's kind of fun and cool, and a cool thing to look forward to. After the midterms, it'll be later in the semester. All right, so this has been diving in for a little bit of the examples and talking through a little bit more on some of the ideas behind designing experimental designs, and some of the different approaches we can take with the best guess approach, the OFAD approach, etc. In the next video, the final video, we're going to talk about implementing design of experiments and what those steps are, and how we can do that before closing out with our example.